Okay, so welcome. This is lecture 4. Very quick announcement. We have the assignment. It's the same thing as Monday actually. It's just you have to pay attention that assignment 2 will be posted usually on Friday. Okay, so assignment 1, the deadline of assignment 1 is Monday next week. Okay. Another thing is about this form, honesty form. I'm still waiting for quite a few of you to sign and submit the form. So please take an active approach and give me the form as soon as possible. Don't. This is something you can forget easily, and I don't want to come back and remind you again and again. Okay. Okay, so a recap from Monday lecture. So on Monday, what did we learn? So on Monday, we learned about quite a few things. It's kind of a little bit historical when we presented the material. For example, now we started talking about thermal equilibrium, and there's the zeroth law. And we established the notion of the empirical temperature. Okay, so we started from there. Then we started to present the main content of the first law. And we concluded that the first law, basically what I written in orange color here, can be regarded as the statement of the first law. So energy is conserved when you take heat into account. And the development we presented on Monday was such that we began by looking at a thermally isolated system and look at what happens to the internal energy when you perform work, and when, in particular, when you perform work by different means, by different ways. And you will find that if you do not consider heat flow, if you have an adiabatic process, work becomes a function of state. And therefore, that allows us to define something called the internal energy. And that is a key concept. This is an internal energy. We didn't really say much about how to calculate this internal energy. And maybe it's useful for me to remind you again that in the spirit of thermodynamics, we don't really want to say too much about the microscopic details. And that is, in fact, the powerful, why thermodynamics is powerful, because it's so general. So we simply have something called the internal energy. And this internal energy is a function of state. Therefore, we use the exact differential for representing the small change in the internal energy. And the differential form of the first law is written like this. And the sign conventions were discussed. Basically, when we have plus for d bar q, we say we transfer heat into the system. And when we have the plus sign for d bar w, we say we are performing work on the system. Okay, and then I presented a table, which I don't show it here, but there is a table with listing the conjugate variables you saw before. And then I told you how to form the work term by taking these conjugate pairs. And one of the important ones we really need to pay attention is this PVT system. And this PVT system can be, if you want to carry out this kind of thought experiment, the simplest way is to imagine a piston which you can move and a cylinder which you can contain your thermodynamic system. Okay, and for PVT system, the change of work d bar w is given by this expression with a minus sign here. Okay, so that's basically all we had last time. And today, and last time we also discussed two cases here. Okay, we discussed two very simple cases of the PVT system or PV system or hydrostatic pressure system. We look at how what happens when you compress an ideal gas in the isothermal manner. Okay, so when you compress your ideal gas, we ask how much work done can we have, and whenever you talk about work done, you need to also discuss whether it's work done on the system or work done by the system. Okay, so this is what we had last time. This is the first example, and the second example, I only changed one word, but the result becomes very different. Okay, if you compress the system adiabatically, this is the result. Okay, so these are very straightforward. And there's one more example which we need to cover. Then we can move on and talk about heat capacity. Okay, maybe I should ask if you have any question for me. And take advantage of the chat room, okay? We are going to communicate this way. Okay, this is the third example which I included in the note. And you are asked to calculate the work done for solid. And how do you imagine solid in this case? So the way to imagine solid is actually you can also use this piston cylinder picture if you like, and that is kind of easier to set up. So the way we imagine the solid is basically the same. We imagine having a piston cylinder system where we can control the force by the piston. Okay, this is our piston. And we are going to put our solid, this is our lump of solid, inside. And we are going to put inside the piston cylinder system some fluid, which is not compressible. So this is incompressible fluid. Okay, so if you try to push this piston by some force F, because the fluid is not compressible, all the work done will be transmitted to your solid here. Okay, and in this case, what we are talking about is still the change of the volume of your solid. So this is the same expression. Okay, so this is the way we imagine the case of solid. Fluid is kind of easy to imagine, but this we have to put in a little bit more effort. And there's a picture in Atkins about this. Okay, so basically this is just what I say. Now for solid, we usually have some assumption if you want to do the calculation. So a typical assumption is this. The assumptions. We are going to look at the change. These are the changes, and the assumptions are when you do this change, before and after the change, your volume is nearly a constant. Another assumption which we usually use is we assume we are going to perform this kind of work, this kind of process over a range of temperature or over a range of pressure, where we can take the compressibility and volume expansion coefficient to be nearly constant. Okay, so these are something you have seen before, and that is because we want to get the result quickly. Of course, if you want to do a more careful modeling, you can remove this assumption. Okay, so what happens when we have an isothermal change? Again, this is a good chance for you to practice how to use partial derivatives. So we know we can characterize our PVT system by, say, pressure and temperature. Suppose we do not allow the change of the mass. If we allow the change of the mass, that is okay. That is something we will also discuss later. And in that case, we allow particle to enter and to leave, in which case we have to talk about something called the chemical potential. So here, I'm going to assume the mass doesn't change, the number of particles doesn't change. And therefore, the volume can be expressed as a function of pressure and temperature. And this allows me to immediately write this expression. You see, I want dV. That's why I spend time working on dV. Okay, so from chapter 1, you know this the change of volume with respect to either temperature or pressure can be written in terms of kappa and beta. So the result is this. This is something you have seen before. This V is here because we like to define kappa and beta to be a fractional change. So therefore, you introduce a volume, and this is the expression you have. And this minus sign is because when you apply pressure, when P goes up, volume goes down, and this gives you a minus sign for this partial derivative, and we don't like it. So we put a minus sign to make this a positive quantity. Okay, and the work done is simply minus P dV. So the work. Now, if I tell you the path, you know you can integrate. Okay, so I'm going to do only one, and you can do the other one later. So I'm going to do the isothermal one. So the second dt will be 0. Okay, so if I do case 1, dt is 0. Okay, so isothermal, I know how to integrate. I just integrate this expression, P1 to and then I need to, sorry, this is, I need to bring this P here. So there's minus P, B, kappa dP. Okay, all the assumptions are here. So V doesn't change, kappa doesn't change. I only need to integrate this, and this gives me the answer. So I will have a half kappa V, and I integrate this P squared. So I will have P, there's a minus, so P1 minus P2 squared. Okay, so you can do the other one yourself, and you have isobaric, so dP is 0. Okay, so as simple as this. Okay, today we are going to introduce the concept of heat capacities. Heat capacities is important because we can measure. So in general, what do we, how do we write heat capacity? We write, now the general notation is like this. So we want to vary alpha. So the meaning here is we want to vary, want to change alpha to see how much heat is absorbed. Okay, and you know, now you might be very suspicious about this expression, this notation here, because we have d bar Q, and sometimes some books write it like this with some constraint here. So the point is, this is in general not well defined. If sorry, there's a message about the previous question. Now, if we assume, now the question is this: if we assume volume to be a constant, why the differential dV is not zero? If this is strictly zero, then I cannot calculate the work done. Okay, here this is a bit similar to what I had in chapter 1. I want this dV to be there for me to be able to calculate the work done, but I do not want to worry too much about how this vary. Okay, so I can approximate this as roughly a constant. So this is an approximation. Back then, I give you a log. That's because in chapter 1, I write this nearly constant, but I didn't really use it. Okay, so if the volume doesn't change, you don't have a work done at all. Okay, and then there's another question. It seems d bar W. You are right, Harry. Sorry, it's a private message, but I somehow identify you. Okay, he said there's a mistake with the sign. So there's a minus here. There's another minus here. Okay, you are right. So so in this case, these two I should swap these two. Correct? Okay, so this should be okay. Let me correct this. This one should be, in my note is correct actually. So this should be P2 minus P1. Sorry about that. So this is an approximation. Okay. Okay, is it correct now, Harry? Right, here as well. Okay, right, sorry. Another thing. This is sorry. I make a now this should be correct now, right? So let me write this now. Okay, very silly. So I have to integrate this d bar W. Okay, so there's a minus sign from here, so I have to integrate minus P and minus this whole thing minus V kappa dP. Okay, so there are two minus signs. Sorry, I make the mistake with this minus sign. Okay, I think everyone should agree now. Okay, I get a lot of private message, but if you don't mind, this kind of thing you can share with the class. Okay, and then in this case, I go from P1 to P2, so this is P2 squared minus P1 squared. I will check the note. I think the note is correct. My handwritten note is correct, but I don't know. I will check the note I posted before. Okay, this is not too much of a problem. You should be able to figure this out. And in case you spot something like this, please always let me know. Okay, the sooner you let me know, the better I can correct the note and post it. And in fact, for the version I posted for chapter 2, I already found a few mistakes, maybe 2 mistakes, but they are trivial. It's not easy to pick up if you are not very careful. Okay, so coming back to heat capacity, what we really want is to have some constraint, just like before. So usually what we are talking about is the most useful heat capacities for us is to vary temperature to see how much heat is absorbed. So usually alpha is temperature. Okay, and when you do this kind of experiment for PVT system, if you talk about heat capacity, you usually have to very right away tell your readers or your audience what you are talking about. Okay, so you need to have a constraint, and the usual constraint is either constant volume or constant pressure. Okay, so the full definition is this. This is the notation I use, and this is also the notation you see in STEAM. Okay, so this is, sorry, one more thing. This is usually written like this. Okay, this alpha here is in the bracket, tells you what parameter you vary. But most people get lazy very quickly and just ignore this bracket T. Okay, so I will also do the same. And the other one, which is very common, is heat capacity at constant pressure. And some book like to write it like this. So they like to write it in this form. You also see this a lot. Okay, but you need to understand the origin of this, and you need to always keep in mind that if I do not tell you how to vary the process, how I vary the process, what is the path, in general, this d bar q is not defined. It's not well defined. Okay. So this is a capital C. Okay, I will draw it like this. This is really a capital C. And this is an extensive variable. So if you change your system size, if you double your system size, the heat capacity doubles as well. Okay, and sometimes it's not convenient to talk about extensive quantity. And very often you see heat capacity per unit volume, per unit mass, or even more common is the heat capacity per mole. So this is also called the molar heat capacity, and the notation is a lowercase c. Okay, CV and CP. Okay, this is really the uppercase. This is the lowercase, and this is usually the heat capacity divided either by the mass, the total mass, or the total number of mole. Okay, and this is the intensive quantity. Okay, quantity. Because after divide by mass or okay, another comment is this. When you do statistical mechanics, you will find that heat capacity defined like this, defined with the constant volume, is actually more fundamental. It's a lot easier to do calculation with heat capacity at fixed volume, when the system is at fixed volume. But unfortunately, experimentally, it's a lot more convenient to have the constant pressure environment. If you pick up a chemistry textbook on thermodynamics, you see a lot of cases like this. Why? Because this is convenient for doing experiment. You take a beaker, you take your liquid here, you open your beaker to air. This is a constant pressure environment because you have your atmospheric pressure here. Whereas for calculation, the reason constant volume is simpler. You can actually try to appreciate it this way. When you do quantum mechanics, you calculate, for example, the simplest problem you do calculation is to find the energy levels of your particle in a box. Okay, and we talk about particle in a box, and you really want your box to be fixed. Although you might not think about it this way, but you see, you get your energy spectrum, you get all this energy characterized by some quantum number n, and you list all these energies. And one thing which is implicit is you have your box size going into this energy level expression. And imagine if you have a volume which is not constant, the energy spacing can change. And therefore, when you do statistical mechanics, you have a nightmare. You have a lot of energy levels to begin with, and these energy levels are changing all the time. So it's very difficult to do calculation there. Okay, so this is one comment, and you will see it quite often. And we can, with a little bit more care, we can of course try to measure the heat capacity at constant volume. Okay, and this is one. Another comment is this. For solid, we do not really need to distinguish between CV and CP. Okay, CV minus CP is nearly 0. Okay, this is a very special case and is a famous case. You are going to have a question in your assignment, and you are going to explicitly find the difference between these two heat capacities for a solid. And there, I would like you to pay attention on some numbers, because if you only do everything using symbols, you will not get 0, you get something here. But the reason that for solid you can approximate the difference to be 0 is because there's one particular quantity which is small. And that particular quantity is small to begin with, and then you take some power of that, so it becomes even smaller. Okay, so this is something when you solve your assignment 2, assignment 3, I don't remember, you will be asked to do this, and please spend some time to appreciate this. And therefore in solid, this is kind of good news. You can do experiment with constant pressure, and you can do calculation with constant volume, and the difference is kind of not significant. Okay, so what do we learn about heat capacity? Why do we talk about heat capacities here in this chapter? The reason is we talk about this internal energy, U, without sorry, what did I do here? Okay, I copy. What I want is to add. We talk about the internal energy U. So first law, let me write first law for you. We have du, which is d bar q minus pdv, and I'm going to write it a little bit differently, and I will have this. Okay, now if I really strictly want my thermodynamic system to keep the same volume throughout the process, then in this case my dV will be really 0. Okay, so this is now I really insist this. I want my dV to be 0. So I want really a constant volume, strictly constant volume condition. Then my dV is 0. Okay, you immediately extract that if I divide by dt on both sides, this is my definition of heat capacity. Constant volume heat capacity. Okay? And this good news is, if you do it this way, it gives you something very fundamental. And that is, you get some feeling about the change of the internal energy. Okay, so this is another way to demonstrate why constant volume heat capacity is important, because it really relates the internal energy. So this expression really relates the internal energy, which is kind of abstract when we introduce it. I just told you there's something like this, but why do you need to believe me? If you really want to believe something, you need to have a way to measure it. So this is a way for you to do that. At least you can measure the change. Okay, so we should also emphasize that this is a change. So if you choose your scale such that you add an offset into your internal energy scale, that remains impossible to determine this way, because what you have is the change. Okay, and this is not surprising. Suppose your internal energy includes some kind of potential energy term, and you sometimes define your potential energy with respect to a different reference point. Okay, if this scale remains the same, the only thing which is meaningful becomes the change of U. Okay, so this relates U by offering you a way to by measuring the heat capacity at constant V. Okay, what happens? What if I don't want constant volume? If I want to look at constant pressure, what is constant pressure? So constant pressure, I will have the definition is this: constant pressure. Let's change color, make life a little bit more interesting. This color is good, I like it. This color. Okay, constant pressure. Okay, the definition is this. I have my CP, which is now I want to talk about d bar Q dt with constant pressure. And unfortunately, I don't have much to do here because I cannot cancel dV. I certainly cannot kill my P. So I have no choice but to write everything down. So this is what we can do, really. You just have to work on this expression again. And this is all you have. Okay, how do I get this? I got this from here. Basically, this is the first law. And constant pressure heat capacity is a bit more complicated. And if somebody thinks this is very ugly, I do think this is indeed quite ugly. Okay, let me take this chance to introduce one thermodynamic potential function for you. So this internal energy, this U, is one of the thermodynamic potential functions. Okay, it's a function of state. And now let me manipulate this a little bit. You see, I have partial derivative with respect to T at constant P for everything. Okay, so this is constant P, so I can put this P inside and multiply the volume V. Okay, so I can write this as partial derivative with respect to T and everything at constant P of U plus PV. Okay? Okay, so then to have a more beautiful expression, I can give this combination a new name, and this is the enthalpy. Okay, not entropy, enthalpy. This is the spelling. And this is one of the useful thermodynamic functions you will see later. Later, you will see it in a more complete picture. I will tell you how to do the transformation to get all these thermodynamic functions and when do we use them. But now this is an opportunity to introduce this. So what you can write is now the aim is, if suppose you want a constant pressure environment, you want something that looks like this expression, more compact. There's no reason why I have to, if I don't deal with statistical mechanics, if I don't worry about this particle in the box problem I described earlier, if I don't need to worry about experiment that is more convenient to keep the constant pressure, there's no reason why volume has to be more fundamental than pressure. Okay, so I can kind of invent something else that looks like this. Then I can, in fact, I do not need my internal energy to be the most fundamental starting point. I can build the structure of my thermodynamics using enthalpy. Okay, in fact, this is not uncommon. You will see this again in chemistry textbook. When they talk about reactions, when they put the beaker in the lab, this is really the condition they care about. So you see a lot of enthalpy. Some of the data books are even written in enthalpy. Okay, so some note about this. Now we define it this way. So we define a new thermodynamic potential function, which we write like this. Really, we define it. I put the definition here. Okay, what do we learn here? U is a function of state, P is a function of state, V is a function of state. So this is also a function of state because everything here is a function of state. Okay, so this is a step function. Which means if you want to integrate this, the differential form of this dh, if you know the endpoints, you know the change. It doesn't matter how you take the path. Okay, so one application to motivate you is, for example, if we look at the PV, sorry, maybe let's look at the phase transition. If we look at phase transition, if we have different phases, let's say this is a TP phase diagram. If we have different phases, when you cross the phase transition, you have something called the latent heat. Okay, so if you go choose any point on this TP phase diagram, and if you go around the phase diagram and cross all the phases, let's say think about H2O, but don't go too far, that you have a critical point here where the liquid and gas cannot be liquid and gas cannot be distinguished. If you just go near this phase coexistent point, this is the triple point, and you can actually write a nice expression relating all the latent heats. Okay, so here the knowledge you use, the tool you use, is the fact that the enthalpy is a step function. So if you use enthalpy is a step function, then you can you can have some expression to relate the latent heats for phase transition. When you cross the phase boundary, there's a latent heat. Okay, so this is the purpose here. We are going to talk about phase transition later, but the purpose here is to convince you that this can be useful. It's not just to make your expression more beautiful. Okay, although I kind of motivated it this way, but this has a lot of application. So this is one. And in your assignment, you will see another one. You will see the parallel between U and H. Okay, if I have, this is 1, if I have constant volume, I have U for this expression. If I have constant pressure, I have this. But you know, from if you if you know how to manipulate partial derivatives, you have plenty of expression. And in the assignment 2, you are asked to explore this a little bit more, so you can practice. Another thing, the number 3, I hope I have time to cover today, and that is about flow. If I push some fluid through a plug, if the plug has some hole, so if I take a tube, if you take a tube, if I put a plug here, but if the plug is completely blocked, then there's nothing to do. Now let's say I have some hole here. So the plug has some hole, which means when I push some fluid from this side to this side, the fluid can be transferred to the other side, and there we can also use enthalpy to explore the physics of this process. So this is 3. Okay, so I'm going to at least you should be aware of the usefulness of enthalpy. Okay, next. Usually, now we have CV and CP. Usually one is bigger. So which one is bigger? Now you can type. Now actually think before you, unless you know the answer already. Otherwise think. What is the thinking process here? Okay, I see 2 different answers already. So that is, then we can have a vote. I think this class is shy. In my previous class, this kind of discussion is usually very active. And the chat is usually to the entire class. Okay, more? Okay, may I ask why? The answer is this. CP is larger than CV. It would be interesting to think about why. The answer is given in the note, in the draft. And if you haven't seen that, you should think about this. Or if you have seen that, you should also think about this and make sure you are convinced. Okay, so the hint is this. You need to think about what happens when you try to raise the temperature. Okay, so if you have constant pressure, if you want to keep constant pressure environment, just like the system I drew, you have the thermodynamic, you have your fluid in an open beaker. All right, when you inject the heat, what happens? Usually your thermodynamic system can also expand. So expansion means you have some work done. Okay, so this is the line of thinking, and then there are some stuff I haven't said, and you can think about this before you look up my note. Okay, the note has the full answer, and this is the result. I convince yourself that this is the case. And from here, we also can define something called the adiabatic index. Adiabatic index. And that is the ratio of the heat capacity. Okay, so I think this is a good time for break. And after the break, I'm almost going to spend the remaining lecture on ideal gas. We want to test all these results using ideal gas. Okay, so I propose let's take a 5 minutes break or so. So come back at around just before 1:30, so we can pick up. And I have quite a few things to present today. Okay, so take a break, and in particular, I would like to reach this point about this flow of the fluid. All right, so welcome back. So from now on, I'm going to talk about the ideal gas. So this is a very special case, and a lot of results we will use is only true for ideal gas. So what is so particular about the ideal gas? So one thing you have is this: for ideal gas, the internal energy is only a function of temperature and nothing else. So this is why this is really what makes all the difference for an ideal gas. Okay, and you can see from here we can get a lot of results that you are I hope you are familiar with. Okay, so this is why we need to test using the ideal gas. Okay, so the first thing is with this. Now, of course, with ideal gas, you also have the equation of state. So if you have ideal gas, this and the equation of states is well known. So for 1 mole, okay, I'm going to do the n here. Okay, or if you are more reading the physics textbook, this is nkbt. Okay, what is the heat capacity in this case? Remember, this is Cp. The heat capacity written before, here, this line. You can use it for the ideal gas and you get some useful result. Okay, so I'm going to write it down first. Basically copy that plus P. Okay, but this is already interesting. So here, because the internal energy is only a function of T, then you actually have something like this. And remember, this term we had before, right? And this, because this is only a function of temperature, you can replace this partial derivative by the total derivative. And with the same reasoning, you can also replace this term by this total derivative. So partial derivative. Okay, now this is only for the ideal gas. So let's do that. This will give you a du dt, a constant p, but we don't care about that anymore, plus something else, right? This p times this partial derivative. And it turns out that this is actually the heat capacity at constant volume, right? Because this is before, when we write heat capacity, we define it as d bar q constant v dt. But that, because it's a constant v, the volume change doesn't matter. And this turns out to be the way to evaluate the internal energy. Remember that we talked about this just 20 minutes ago. So this term is heat capacity at constant V. Okay, and the second term we can do a little bit more. If you look at this equation of state, PV is nkbt. I'm going to use this term, the later one. So this express V in terms of T, and if you have constant P, this turns out to be, this whole partial derivative will give you n times Kp divided by, n times Kb divided by P. Okay, so you cancel this. This is using the equation of state. You get Cv plus nkb. Okay, so this is the result. This is the standard result, famous result actually. So Cp minus Cv is nkb. Okay, it might not be familiar to you. That is because maybe you don't read it this way, right? You don't write it this way. And usually what you do is you discuss 1 mole for 1 mole of ideal gas. Okay, in this case, you have Cp minus Cv, and that will be the Avogadro number times Kb, and this becomes R. This is maybe something you are more familiar with. Okay, and this is nice because if you know one, you automatically know the other one. And there's a figure in the note. I'm going to bring it here. So this is for nitrogen gas. And you can see it doesn't matter how you vary your CV, your Cp is always differ from Cv by this constant amount R, right? This R is about 8.3. If you add this 20 to add this curve by 8.3, and you take this curve of Cp. Okay, so this is the data for nitrogen gas. Nitrogen gas. Okay, another thing is when you write it this way, you see your heat capacity. Sorry, I didn't say it before, the heat capacity. So let me go back a little bit. When I first introduced the heat capacity, I should have said that heat capacity should have the unit of joule per Kelvin. Okay, so this is heat capacities. And this is intensive quantity specific heat capacity. Another thing I didn't say, I forgot to say, but it's rather important, so pay attention. And this specific heat capacity is heat capacity divided by the system size, something to do with the system size. For example, the mass or the number of mole. And very often people don't like to say the full term. They don't like to say specific heat capacity. They always say it, they always kill the last word and use specific heat. And somehow this is everywhere in the literature, in all kind of textbook, in all kind of published journal articles. But please bear in mind, this is not heat. So this is really heat capacity, it's not heat. Okay, it doesn't take the unit of joule. It takes the unit of joule per Kelvin per mole or joule per Kelvin per kilogram. Okay, so this is not heat. This terminology is very unfortunate, but there's nothing much I can do. Okay, so when you write it this way, you see this is the units is also important. When you talk about 1 mole, then this is technically the molar heat capacity. Okay, so my tips to you is you always look at the unit. This is how we navigate here. Okay, and therefore this kind of, because of the quantity is written like this, although conventionally people write it with capital C, this is really an intensive quantity. And people like to reserve the lower case really when you divide by the mass. Okay, I still want to continue to talk about the ideal gas. This is a famous result, you know, and there are a few more famous results that we can share. We want to look at the ideal gas expansion again. Okay, we want to look at expansion. So let me write it here. Actually, we want to look at two kind of expansions. So one, the simplest one is isothermal expansion. Isothermal means the temperature doesn't change. And in this case, du is 0. Okay, now this is important. If you don't immediately get this, it's fine at this stage. But later on, you need to really appreciate this quickly. Why do I say du has to be 0 for isothermal expansion? The reason is we have an ideal gas. This is because U is only a function of temperature. If I'm not allowed to change the temperature, du has to be 0. Okay, so if you move along the isotherm, you have always have this condition. Okay, and that is kind of fun because you apply first law. You will see if you have expansion, there will be some kind of work, right? If your gas expand against the piston, you are doing work. The work done is by your gas. Okay, but the internal energy doesn't change. Okay, and it means I have to take energy from somewhere, and this energy has to be provided by the heat. Okay, so I need to allow some kind of heat flow. So according to the first law, this is what happened. Because du is 0, so dq exactly compensates d bar w. So d bar q is the opposite of d bar w. And d bar w is minus PdV, so we have this result. And therefore, you can ask yourself, how much heat do I have to supply if I want to have some expansion from volume V1 to V2? Okay, so this is very different physics, but calculation is identical to what I calculated at the end of last lecture, example 1, okay, with a sign difference. But the story, the way I put this is different. And back then, I didn't say all this. Okay, so you use the equation of state, and you get RT is log of V2 divided by V1. Okay, now I'm a bit afraid that I make a mistake with the minus sign. Let me check. So I have P. This I use the equation of state, so I will have 1 over V here, and I have RT outside, so 1 over V. This is correct, right? Where's Harry? Harry still here? Okay, so if I have an expansion, V2 has to be larger than V1, right? So this is larger than this, so the ratio is larger than 1, so log is positive. So if I have an expansion, this is positive. Okay, so if I have an expansion, delta Q has to be greater than 0, has to be positive, which is correct, right? Because if you have an expansion, your system is doing work on the surrounding. So according to our sign convention, this is negative, right? The work done would be negative. Okay, the work done by this, the work done on the system will be negative according to our sign convention, and therefore we have to supply, we have to add some heat to compensate for this in order to keep du to be 0. Okay, so this is all good. Okay, now I'm going to talk about another type of expansion. Now, by the way, let me also write it here. There's a name for this. This is also called Joule's law. The fact that for an ideal gas, so for your easy reference, for an ideal gas, the internal energy is only a function of temperature. Okay, the second one is another type of expansion, but this time is adiabatic. Okay, I think you maybe you can sense where I'm going. It's still the ideal gas. I need to talk about this type of expansion because later I want to build my Carnot cycle. Very soon I want to move to heat engine. So this has to be mastered before. Okay, adiabatic expansion. This time du cannot be zero because this time d bar q has to be zero instead. Okay, so there's no heat. So something else is zero. That something else becomes d bar q, and du has to take this expression. Du becomes d bar w, which is minus p dv. So these are all first law, spatial case of first law. First law. This is first law. The simplest first law I can do here. First law, once I combine with second law, it will be a lot more powerful. I can do many things. But right now, these are the standard thing to do. Okay, so again, for an ideal gas, I can write CV, capital C is this. Okay, and because this is an ideal gas, again, the same line I am copying again. So this is the same as this and the same as the total derivative. This constraint doesn't matter anymore because they cannot change anyway. They can change, but it doesn't affect your internal energy. Okay, so if you look at this line, then you can write something. You can write this. You can write du is CV dt. Okay, so let me put in red color for you. This is a very common mistake for some reason. It's very strange, but we see this a lot. And this is only true only for an ideal gas. Okay, Blundell has one example talking about this. If you don't have an ideal gas, you might have a situation like this, but you cannot just use it right away. It would just, it so happen that maybe the other variable you choose is the other term. So in general, this is, you can only use it directly if you have an ideal gas. The reason is very simple. U is a function of T only. Okay, so this is my du, and du is pdv according to here, minus pdv. Okay, so now I put in the equation of state. This is RT divided by V dV. Okay, now this is all I need, and I can begin to play with this. So what I would do is I'm going to integrate. I'm going to look at this line and this term and this term here. So I'm going to integrate with respect to temperature. So if I look at this, I have to move this T here. 1 over T dt, CV times 1 over T dt is minus R 1 over V dV. 1 over V dV. Okay, so I'm going to look at this one and this one. Okay, let me put it as a definite integral. I'm going to look at the expansion. I'm going to look at the volume change from V1 to V2. So this will be the corresponding T1, T2. Okay, so I'm going to write a long expression. This will be 1 over T. You integrate 1 over T, so that gives you log T2 divided by T1. And I have minus R on the other side. I'm going to move this CV to the other side. and I integrate again, I have V2, V1. Okay, I have my minus sign here. Okay, what is this? What is this thing? This is 1 minus the adiabatic index, log of V2, V1. Okay, so this whole thing is the adiabatic index. It's related to the adiabatic index. Okay, why? Why? No, I will write here. I don't want to interrupt the flow. I hope you okay. It's not long. I will write it now. Adiabatic index by definition is this. Okay, these are all capital C here. All of these are capital C. But we already know for an ideal gas, this is CV plus R divided by CV. Okay, so this is 1 plus R divided by CV. Okay, so you move this to the other side, move gamma to here, you have 1 minus gamma. Okay, so you have log of this is the same as log of this raised to the power of 1 minus gamma. So that gives you so that gives you T1 times V1 because it's 1, this whole thing raised to the power of 1 minus gamma. So you can write T1 V1 gamma minus 1. It's the same as T2 V2 gamma minus 1. Okay, so this is the condition for adiabatic change. And this is maybe not something you remember well. Certainly, I won't be able to remember this after a few weeks. So if you plug in the equation of states, this is equivalent to PV to the gamma is a constant. Okay, this is what you remember. Okay, so you have your adiabatic expansion, and that has to follow this. Okay, nice. Okay, so if you have your PV diagram for an ideal gas, now you have the full picture. If you have an isotherm, this is an isotherm. I will draw something like this. Let's say this is a T2. So you know how to draw your isotherm because you know the equation of state. So this is isotherm. And you can look at the expansion. So expansion means you are traveling from left to right. And this has to, if you have something like this, if you travel from left to right, according to our calculation earlier, you have to supply heat. So let's say we will supply heat, Q2. Okay, I'm going to keep this notation. And you can easily reverse the logic, right? So I draw another isotherm as at T1. If I draw my arrow like this, which means the process is a compression instead, then you will generate heat. So this is heat give out. This is Q1. This one is good. Okay, and if you have adiabatic change, usually you will have, suppose you have one adiabatic change. Adiabatic change is the line on the PV diagram is called adiabat. So if you have an adiabat crossing an isotherm at the same point on the PV diagram, it can be shown that this is always steeper. So the slope, the local slope here is always steeper than this. So you have to draw something like this. Okay, so this is adiabat. Okay, it can be shown, of course, somebody has to show it. And that somebody turns out to be you, and you will show this. Okay, so you can have adiabat like this, and you can have another adiabat. You can have many adiabats, and this is another one. Okay. So in general, now if you start from A and you travel like this, if you start from A, you travel like this back to A. If you travel from A back to A, because the internal energy du, and internal energy is a step function, du has to be 0 in this process. Okay, so this is a cyclic process. And this is actually the basis of a heat engine. Right, we define this, and don't forget, thermodynamics was very important because people wanted to understand heat engines. And this is actually the consequence of the first law. So from the first law, you have this is d bar q plus d bar w. Okay, and because when you go through this process from A to B to C, okay, let me label this A, B, C, D, A, A, B, C, D, A. When you go through the whole process, this has to be 0. This now be careful. I'm sure this is not much of a problem. This du equals 0 is not the same as this du equals 0. Okay, this is because you have an ideal gas. Here I'm talking about something very general, because u is a step function. U is a step function. If you come back to the same point, du has to be 0. So this is the basis of the heat engine. And that's why if you want to extract some work done, you have to have some injection of the heat. That's why you usually see something like this. You have a diagram telling you, okay, I'm going to have an engine which I want to extract heat from, usually it's called Q high, T high. So here T high is T2, T1, and I'm going to extract some heat from here, Q2, right? Heat goes into the system, and I have to dump some heat out, and heat went out to the from the system. And for this to be useful, I better be able to extract some work. Okay, and this is all simply governed by the fact that you drive your engine from one state back to the same state. So you have this cyclic process. So for each cycle, you have this. You can draw an equivalence diagram like this. Okay, so this is the basis of the heat engine. So from here, you can already say something about the heat engine. And if you draw it like this with exactly 2 isotherm and 2 adiabat, this is a Carnot cycle. This is a Carnot cycle. And if the engine is based on a Carnot cycle, this is a Carnot engine C, which is the most efficient engine you can get. Okay, so this is actually very important, because by studying all this engine, by talking about efficiency, people discover the second law. Okay, that's why you see all this in a funny way to say the second law. Suddenly you have all these engines coming in. They talk about efficiency, they talk about whether one engine is possible or not possible, and you have all these statements built upon engines. And you can appreciate this by looking at this diagram here a little bit more. Okay, so this is coming up soon. This is next chapter. And then this is going to lead us to the second law. Right? From all this efficiency argument, we discovered there must be something interesting about this efficiency. Right? Why do we have this kind of limit? Okay, basically this is all in the note, but I want to give you another piece which I will post as a supplementary material. Okay, this is about the fact, about Joule's law, about this fact. Okay, I think this is kind of cool, and we should spend some time to look at this. And as with all these thermodynamics arguments, they are kind of based on experiments. So this is kind of one experiment Joule and co-workers conducted before. And that is to look at a free expansion. This is the picture. So suppose you are able to come up with a system like this. This is a adiabatic wall. So you have a thermally isolated system with a partition. So on one side of the partition, you have your gas. On the other side of the partition, you have vacuum. Okay, so this is the setup here. And the idea is this partition, suppose you can remove it, what happens to the final temperature T1? Okay, initially you have a volume V0, you have the same amount of gas, and you have T0. After this partition is removed, what happens to the temperature T? Okay, this is another type of expansion. We talk about a lot of expansions here. Yeah, this is another type of expansion, and this expansion is kind of unique. Okay, what is this expansion? This expansion is free expansion for the reason you will see soon. Okay, so let me write down what we want to measure. So after the partition is removed, we want to ask what is we want to measure, try to measure, or Joule tried to measure T1 minus T0, and this is the this is the experiment that gave this conclusion. Okay, so what do you actually measure from this discussion? What is the partial derivatives we are interested? Any idea? You can type. If I want, I already described the experiment, right? After I remove the partition, I want to measure this. So if I want a partial derivative, what is that? And what is the constraint? Anything? Okay, good. More? Okay, this is an experiment designed to evaluate this partial derivative. Okay, and what is the constraint? What goes here? Look at this system. Now, this one you can definitely type very quickly. What is the constraint? More? Keyword is free. Yeah? This is important, free expansion. Okay, the constraint is this. This is a very interesting one. This is, the constraint is constant U. Yes, P is 0. Correct. So there's no work done. Right? P is 0, free expansion, there's no work done. Adiabatic wall, there's no heat flow. So according to the first law, u has to be constant. There's no way to change the u. Okay, so this is the partial derivative. At least he tried to measure. Okay, so there's the rest is really the story. You just have to understand. The key is to understand this is the partial derivative we want to measure. And the experiment, actually, this has a name. This is what is the symbol? Let me. Actually, is there a symbol for this? This has a name. This is called Joule's coefficient. Okay, so the idea is this. Now let me present this. You can actually this is fun. Okay, let's write u as a function of t and v. Okay, and from here, you know, you can have the relationship between the partial derivative. So you have this. Sorry, this u v. I don't want this. Sorry. So t first. Okay, so we have this reciprocity theorem. And let me tidy this up to express this in terms of the other two partial derivatives. I can write this like this. Minus okay, correct. So this is really just take from here and I move this term to the other side, I move this term to the other side and take the inverse. I use a reciprocal theorem. Okay. So I have this relationship. And for the PV system, we know CV is this. Right? We have seen this today. So this is the heat capacity. Where is it? This one is the heat capacity. Now, be careful. Right now, I do not assume an ideal gas. This is the point. I do not assume an ideal gas. Actually, I want to verify this. So I want to show this for an ideal gas. If I assume this, then there's nothing much to do. Want to show this for an ideal gas. Okay, so I just write all these partial derivatives as accurately as I can. Okay, so this turns out to be minus 1 over CV, right? This is here, 1 over C constant V, partial U, partial V, and T. Okay, so far so good. Here I really just manipulate all these partial derivatives. And now here is the result, which you need to begin to pay attention. Here's the physics. Okay, so I'm going to put it in a way which is useful for us. I will have a minus CV, and I will have the Joule coefficient. Okay, what is the meaning? The meaning here is this. I'm going to go and do this experiment, or Joule went on to do this experiment. if you can measure the change of temperature, this T1 minus T0, after the free expansion, and you know the volume change, you know the partition, the position of the partition, and you know how much expansion you get, so you know your volume change. And heat capacity, you will be able to estimate in principle. And if you can measure the temperature change, at least you know this is non-zero. Okay, do you get this point? If experimentally you are able to detect a temperature change after the partition is removed, then this has to be finite, and heat capacity is finite, then this is finite. So your internal energy as a when the change of the internal energy when the volume changes can be determined. Okay, but experimentally, with an ideal gas, the finding is this is zero or very, very small when the gas is very dilute for an ideal gas, which means if you are able to approximate your thermodynamic system as an ideal gas, this is zero. Okay, so when this is zero, it means you, when do you have this case? Now you assume u as a function of T and V, right? So when partial derivative of u with respect to V is zero, it means u cannot be a function, u cannot be a function of V. Okay, so you go back to your assumption earlier, you assume u is a function of T and V. But now the partial derivative with respect to V is zero, so u can only be a function of T. So this is the conclusion. So u is only a function of T. Okay, so this is experimentally. All right, but I want to push a little bit more because this is very neat. We can also try to prove it theoretically. Okay, so we can try to, okay, I say theoretically, it's not very theoretical, but theoretically, what can we do? Okay, I'm going to take the result from your assignment 1. From assignment 1, I asked you to show something, so I'm not going to show for you, but I asked you to show this. If you are very observant, you will see that this is the same thing, same partial derivative. I asked you to show in your assignment. Actually, some of you already had it in your assignment. So this is true. I asked you to show it by, there are many ways to show this. The way I explicitly ask you to do is to take 1 over T as the integrating factor for d bar q. That's my demand. I asked you to show it this way, and you gave me this result. Okay, now this is very general for any PVT system. So for any PVT system. Okay, but this result is true for an ideal gas. Okay, so for an ideal gas, what else can you do? So for an ideal gas, one thing you can do is you can plug in the equation of state for here. Okay, you have PV is nRT, right? So you have PV is nRT, and then you rearrange this, you will get basically the whole thing, T times this becomes P for the first term, after you plug in the equation of states for an ideal gas. So here you use equation of states of ideal gas. Okay, you have P for this first term and you have this P here, so you get 0, 2, which is what we find. So this is what Jill did the experiment to find this, and this is what we do that you can do when you already know how to write this expression, which you know, because or if you don't know now, you know later when you finish your assignment 1. Okay, so this is very neat. This is one experiment that he came up with to prove that the internal energy is only a function of temperature. And when you learn more statistical mechanics, you know how to write this, right? You have you have to worry about the degree of freedom, whether this ideal gas is monatomic or diatomic. Then if it's diatomic, the gas can rotate about the center of mass. You have more degree of freedom. You have to add all this degree of freedom up. And all of them, the net result will only be some numerical constant times temperature. Okay, so you should you will definitely see this later, but I suspect you have seen something like this before. Okay, so the lesson from today's lecture is thermodynamically, we have a way, without knowing the details of the interaction, without knowing the microscopic details, to extract things like this, which is very powerful. Okay, and I think this is the end of my lecture hour, but I would like to push on a bit, so you are welcome to stay. In any case, this is going to be on, the video will be uploaded. It's a bit more convenient for me if I can finish this, even if I overrun a bit. Okay, this is something you can read, you can watch by yourself later, but you are welcome to stay if you want, okay? All right, so I'm going to present a slightly different way to do this experiment, and also take the advantage to introduce, use the thermodynamic function enthalpy a little bit more. Okay, I will try to be brief, but this is rather cool. Okay, suppose you have an adiabatic wall again. This time, imagine the wall is also closed here. I don't draw it here, but just imagine your whole thermodynamic system is enclosed in an adiabatic wall. Okay, you can imagine this to be some kind of flow through a flow impedance. So this is a plug. This is a flow impedance, which means it will impede the flow. If you remove this, then the flow impedance is 0. Imagine this to be some kind of resistance. Okay, so if you push, if you want to discuss some a volume element, let's say a fixed amount of gas, going through this process, a model system for you to think about this is you can imagine having a piston here that you can apply force to allow you to simulate some kind of pressure P1. Okay, in reality, this could be some kind of pump. You see, you can have a pump here. You can connect this outlet to a pump, and you can connect the inlet to a compressor. Okay, the idea is this. What happens is when you can actually imagine in your mind, right? This is kind of reasonable. When you do this process, what happens is because of this impedance, you will have an expansion when you go to the other side. Okay, this kind of resists this flow, so pressure on the left is higher than pressure on the right. Okay. So in order to mimic this pressure, to model this pressure, we artificially add a piston, which allows you to kind of imagine what happens to the same mass of gas particle. Okay, so the objective here, again, is the same. We want to measure temperature change before and after going through the plug. Okay, we want to measure, so we want to measure the objective is a variation of the Joule's experiment. So we want to measure T2 minus T1. And this is an expansion because volume will change. Volume 2, V2 will change. And same as before, we will have no heat flow. So we can have this condition D bar Q is 0. But the reason I want to talk about this is because now you don't have this du equals 0. You have something else, which is very cool. Okay, you can calculate the total work done. What is the total work done on the system? Okay, I will choose on the system. Okay, the total work done on the system will be this one, this contribution plus this contribution. But here, clearly, because this pushed the piston away, this is the work done by the system. So you, at some point, you will have a minus sign, so be careful. Okay, so I'm going to calculate the work done, W1. Suppose I'm able to keep the pressure constant. This is something which you have to imagine a little bit more. As I say, in reality, we are going to connect this kind of setup to a compressor on one side and to a pump on the other side. You can imagine that you move the piston in a way that you keep the pressure constant. Okay? So in this case, you integrate the work done, which is minus PdV. But because I want the pressure to be constant on the left-hand side, this becomes P1. And the volume, initial volume is V1, and the final volume is 0 once I finish this process. So what happens in the plug is very complicated. But we don't need to worry about this. We just have to worry about the initial and the end point. And likewise, we only want to worry about what happens to the initial and the end point. Okay, so this will give you a P1, V1. And you can repeat for W2, then you get minus P2, V2. Remember, this because there you are integrating from 0 to V2. 0 to V2. Okay, so the total work done on the system will be W1 plus W2, which is minus P2, V2. Okay, so let me write it in a more neat way. So this is the total work done. P1, V1 minus P2, V2. Okay, and you can also ask about the total change of the internal energy in U. And this will be again, this will have different sign because you add internal energy to one and you remove the internal energy from the other. So this is U2 minus U1. And there's no heat because of the adiabatic condition. So this work done has to balance the change in U. So I will have, in this case, because these two must balance each other, I can have U2 minus U1 has to be the same as P1 minus V1. Okay, let me write this. P1 V1 minus P2 V2. Okay, so I can rearrange it. I put everything with U1 together. So U1 plus P1 V1 is the same as U2 plus P2 V2. And this gives me the condition of constant enthalpy. This is my definition of the thermodynamic function enthalpy. So this process conserves the enthalpy. Okay, and we can say more about this. For example, if you know how to write this U1 for flow, for flow through a tube with different height, this actually leads to the Bernoulli equation. But we are not going there, okay? So you should probably know that from here, we already have the PV term. But in the Bernoulli equation, there's kinetic energy density. That is to say, you need to learn how to write U1. You need to decouple this U1 into this kinetic term and the potential term to take into account that your tube, the fluid element can flow from one level to a level of different height. So that will lead to Bernoulli equation. Okay, but our aim is to calculate this. Okay, so our aim is to calculate this. And what is this? What is the partial derivative we want to calculate? Now, what we want to calculate here It's very similar to what Joule's expansion, free expansion is doing, but now in principle, this is similar mathematics. So what we want to calculate is the change of temperature, but this time it's not because of the free expansion. This time it's because of the change of pressure. We have two pistons that we can model two different pressures at the outlet and inlet. Okay? And what is the constraint? The constraint is before and after the process, I will have constant enthalpy. So this is what we want to do. And this thing now has a symbol. Actually, the one before also have a symbol, but I forget. This is the Joule-Thomson coefficient. Okay, and then you play the same trick of the cyclic, the reciprocity theorem. You will find, so if you use the same reciprocity process, identical mathematics, you will find something like this. Okay, I'm nearly there. Just bear with me for a little bit longer. You can see this is a very similar expression. And this is what experimentally sought out to measure partial T with respect to P, now this one. And if you have an ideal gas flowing through this setup, you find that this is 0. So this allows you to conclude that for an ideal gas, H is a function of T only. Okay, so this is the enthalpy treatment. I gave you the internal energy treatment, and that is a famous Joule's free expansion experiment. But this is not too much of a hassle to add. So this is, again, another way to show this result for an ideal gas. Okay, I think I have to really stop here. And thank you for your attention.